Hello everyone. Today in this lecture session, I am going to discuss about the most important topics under cyclic course, that is how to design the cyclic encoder based on the shift register circuit, and how to find the code word by using that encoder circuit operation. Similarly, how to decode by using cyclic codes, and how to design the syndrome calculator, how to find the syndrome, based on that syndrome, finally how to decode the error vector, or how to decode the final message bits from the received error vector. Okay, so all these things will be discussed in this particular lecture session. So now let us see the basic block diagram for the encoder for a cyclic course, and all of you remember that these encoder circuits are designed based on the systematic cyclic code form. So assume that all the things what I am going to discuss here are all as based on systematic cyclic codes. Okay. Now let us observe what is the basic block diagram of a encoder for a cyclic course. Later we'll discuss about the decoder. So in the encoder, you can clearly observe there will be some kind of blocks which are mentioned as some notation like P1, P2 and so on. So these are nothing but the flip-flops. These are nothing but the flip-flops. So here don't worry about what is these representations and everything. No need to remember. I will tell you in a very easy way. So here these let us consider these let us find some observation by looking at the block diagram. So what do you observe? There will be some blocks are there like this. So these are nothing but the flip-flops, and there will be some feedback connections. So these feedback connections are mentioned with notations like G1, G2 and so on. So already we know that G1, G2, G3 are nothing but the generator polynomial coefficients. Since the generator polynomial equation is given by g of x is equal to 1 plus g1 into x plus g2 into x square plus and so on, the last term is x power n minus k. So this is already we observed in the previous lecture that the generator polynomial equation for a cyclic code, for a n comma cyclic code, is represented with starting from x, starting from 1 to the last term, that is x power n minus k. In between these two terms, there will be a generator coefficients which are multiplied with x terms. Okay, but here for 1 and x power n minus k there are no coefficients. Only the coefficient starts from here, that is g1 into x, and then increase. So that is g2 into x square, g3 into x cube, g4 into x power 4 and so on. So whatever may be the number of coefficients that multiply with the x terms and continue up to the last term, that is x power n minus k, but don't multiply with any coefficient for this last term. So the first term and last term are common for any generator polynomial equation, but in between the coefficients, depending on the number of coefficients, this equation may be changes. For example, a g of x can be like 1 plus x square plus x cube. That means start from 1 and end with x cube. So the last term indicates that the power of this x term, that is 3, that is indicating that it is n minus k. That means the number of particles are 3. In between these two only the remaining terms are there, that is x square term. So 1 plus g1 into x, but g1 into x is not there, so you can assume that g1 is 0, plus g2 into x square, that term is there. Instead of g2 here it is 1, so 1 into x square, that is x square. So like that, whether the 1 is multiplied with x term or 0 is multiplied with the x square term. So based on that multiplications, we can assume that these generator coefficients are either 1 or 0. If it is 1, so there will be a short circuit connection. If the coefficient is 0, so there will be open circuit connection. So there will be no feedback connection. And also you can clearly identify that every flip-flop output is making an XOR operation with the feedback element. Again, second flip-flop output also make an XOR operation with the feedback connection. And again, third flip-flop output is also make an XOR operation with feedback, and so on. And then the final flip-flop output is making an XOR operation with the message bits. Let us assume this is the message bits. Okay, don't worry about the representation. Let us assume there will be some message bit sequence like ones and zeros are applied here. So each message bit is making an XOR operation with the last flip-flop output, and finally the result will be connected to the first flip-flop as well as with these feedback connections. Let us assume this gate will be always on whenever the input message bits are operated. Okay. Then after all the message bits are received here, then this switch is connected from this point to this point, so that the contents of these flip-flops will be come to here as a code word after the message bits. That means first message bits will come and then the parity bits will come from this flip-flop contents. That means the flip-flop contents after all the shift operations are nothing but the parity bits. So these parity bits will come like a systematic code. So first message bits are coming and then the parity bits are coming. So the code word is nothing but a systematic code. Now we'll see how to design the encoder circuit for a particular generator polynomial equation which is given, and how to identify the flip-flop contents, and how to connect the message bits, how to find the code word, how to perform the shift operations. Whatever things involved in this will be explaining in a very easy way. So don't worry about this particular lengthy block diagram. No need to remember this also. Right? Now let us go with the direct examples. For example, if a problem comes like this, as a design the encoder for a 7,4 cyclic code with generator polynomial, that is g of x is equal to 1 plus x plus x cube. Okay, we need to design the cyclic encoder for this particular generator polynomial equation. So generally encoder is designed based on this generator polynomial equation only. That means if you know this is just an equation of generator polynomial, then you can completely design the total encoder diagram. And after designing what they are asking, and then find the code word for the particular message, that is 0101, by using this encoder. Okay, so in this example I will explain how to design this encoder for this given generator polynomial equation, and then we'll see how to find the code word for the given message by using this encoder operation. I will explain the operation also, and I will find the code word for a given message. Now, what are the steps involved while designing the encoder for a cyclic code? So I will explain in a very easy way with 3 steps only. Okay. So under step 1, the first thing is draw the number of flip-flops required in the encoder. Okay. Suppose if you observe that there are 3 blocks are drawn like R0, R1, R2. Let us represent with the notations. This is the first flip-flop, R0, R1, R2. So I identified that 3 flip-flops are there in this particular encoder diagram. So how to identify the number of flip-flops? How do I know only 3 flip-flops are there in this? So to know that, the number of flip-flops are equal to the number of parity bits is equal to n minus k. What is the formula for number of parity bits? That is n minus k. If it is given that it is 7,4 cyclic code, so n minus k is equal to 7 minus 4, that is equal to 3. So the number of parity bits is equal to the number of flip-flops. So that is equal to 3. So I identified there will be 3 flip-flops that must be connected in the encoder diagram. So before that, just draw these empty blocks as 3 flip-flops. 1, 2, 3. Just draw 3 blocks. That is the first step. After identifying the number of flip-flops, next step is make an XOR operation of last flip-flop output. Make an XOR operation of last flip-flop output with message input. With message. Let us assume this is the message input. Whatever may be the message we are applying here, so that must be connected here. So one bit by bit, it will be make an XOR operation. So the last flip-flop output, make an XOR operation with input, and finally connect this XOR output with the first flip-flop. Connect it to the first flip-flop input. That's it. So this is common for any encoder designs. After identifying the number of flip-flops, then the second step is always common, that is last flip-flop output, make an XOR operation with input, and final output must be connected to the first flip-flop input always. Whatever may be the example given, so do this all the time. For example, here there may be 5 flip-flops, so last flip-flop must be make an XOR and then connect to the first flip. So this is the second step, right? Next, third step will be connecting the feedback connections here in between the flip-flops. How to connect the feedback connections with XOR operation, right? As like this, how to make feedback connections here. So this is the first step, identifying the number of flip-flops, and second step is make an XOR operation of last flip-flop and connect it to the first flip-flop, and third step is connecting this feedback connections. How to do this? In step 3, first we need to identify the number of coefficients from the generator polynomial equations. Okay, depending on number of coefficients, that is G1, G2, G3 and so on, there will be such number of feedback connections. Okay, so the number of coefficients can be identified from this polynomial equations. So it is given that it is 1 plus x cube. So try to compare with the standard notation, that is, what is the standard notation of g of x? 1 plus g1 into x plus g2 into x square plus and so on. The last term is x power n minus k. Similarly, represent this in the form of this, that is 1 plus g1 into x. So x term is there. In place of g1 there is 1. So 1 into x plus no x square term. So that in place of this 0 into x square plus, so x cube term is there, that is x cube. So you already know that there are no coefficients multiplied for 1 and x power n minus k. That means the first term and last term are as it is with no coefficients. In between only there will be coefficients. So what are, how many number of coefficients are there between 1 and x cube? G1 and G2 only there. So here when you compare this one, G1 is equal to 1 and G2 is equal to 0. So we identified that there will be two coefficients. One is G1, another one is G2, and the values of these coefficients are G1 is equal to 1, G2 is equal to 0. So G1 is the first coefficient which must be connected to the feedback after the first flip-flop. G2 is the second coefficient, automatically that will be connected after the second flip-flop and so on. But here we know that G1 is equal to 1. If any coefficient is 1 under this feedback loop, then only connect this feedback path again to the output of the first flip-flop and make an XOR operation. Okay, if there is a coefficient, then only there is a connection, and connect the first flip-flop output and make an XOR operation. The XOR output will be connected to the second flip-flop. That is the operation. So connect this, make an XOR operation and give to the next flip-flop, and the next flip-flop will do further operation. So if there is again another coefficient, if G2 is equal to 1, then again there will be a connection and XOR operation connect to the next flip-flop. But here G2 is 0. So if G2 is 0, this will be disconnected. There is no feedback connection. It will be open circuited. If it is open circuited, no need to connect this. So if there is no connection, so there is no need of XOR operation. So that's why this operation will not be there, so that the flip-flop output for R1 is directly connected to R2. That's it. So that's very simple. This is the complete diagram for encoder for a 7,4 cycle code with this particular generator polynomial equation. So that's it. Now the task is how to find the code word for a given message. So apply the message here and how to find the final code word. The code word must contain 7 bits, and that 7 bits is a systematic code, so that first 4 bits must be a message bits and next 3 bits must be parity bits. Now let us see the operation of this particular encoder. So I am replacing the same encoder here. Okay, and how the output is connected? First the output is connected to this position 1, that is to the message bits, so that in the encoder output, whatever the maybe the message bits, that is 0101, the same message bits will come as it is, because it is directly connected to the message bits initially. So 0101 will come. After that, the switch is connected to position 2, that is it is connected to the flip-flop outputs, so that the contents of these flip-flops one after the other will receive here. So these are nothing but the parity bits. So to calculate these parity bits, we need to identify what are the flip-flop contents inside R0, R1, R2. So one after the other, it will come out from there at this particular point. So to find the shift register contents or flip-flop contents after all the shift operations, we are using this tabular form to explain. Okay. So here we know that there will be 3 flip-flops are there. So whenever you are applying each message bit input to here, based on each message input bit, these shift register will perform one shift operation, one write shift operation. Again, if you apply another bit, again the bits will be shifted right one bit. Again, if you apply message bit, one shift operation will be performed. Okay. So I think you already know that how to draw this block diagram. So this is completed. Now let us observe what is the operation involved in this. Based on this operation, how to find the parity bits, how to find the parity bits finally, and then write the parity bits after the message bits so that it will be a final code. So to calculate the parity bits, we should identify the shift register contents after all the shift operations. Since 4 bits are there as a message bit, so there will be 4 shift operations. So the final contents of the flip-flops after 4 shift operations are nothing but parity bits. Okay. Now let us see. First write input bits. What are the input bits are there? Just write in a column like first, this is the first message bit, second message bit, and so on. Next, write register content before shift operation. That means the previous values. So what are the previous values of these flip-flops? Initially, let us assume the previous values of the flip-flops are 0, 0, 0 in reset condition. Next, what are the shift register contents? That means the flip-flop contents after shift operation. After shift operation. That means after applying input, the flip-flops will perform one shift operation. Okay. So after shift operation, what are the contents of these 3 flip-flops? So how to find the contents? Okay. So which information will be stored in this here? That comes from whatever may be the input that is applying here. So what is the input that is applying to R0? This is the input. So where it is coming? From where it is coming? It is coming from here. After this XOR operation. What is this XOR operation? This is the XOR operation of this M and then R2. So M XOR with R2. So M XOR with R2. If you perform this XOR operation, so that result will be shifted to this R0 content. So that's why after shift operation, I am representing with R0 dash, R1 dash, R2 dash are the new contents of these 3 flip-flops after shift operation. Okay. Similarly, what is the content of R1 after the shift operation, that is R1 dash is equal to, how to find this content? So this content is coming from this input. So how to calculate this input? This is nothing but the XOR operation of this and this. What is this one? Again, this input is coming from this path, which is nothing but again M XOR with R2, again XOR with R0. So M XOR with R2, XOR with R2. Next, what is the flip-flop content of R2 after shift operation, that is R2 dash? So from where the input is coming? The input is coming directly from R1 without any operation. So that R2 dash is directly equal to R1. That's it. Okay. So just by using these formulas, calculate the flip-flop contents after every shift operation. Now, if the input is 0, if all the contents are assumed to be 0 initially, then the next values are R0 dash is equal to M XOR with R2, that is M, this is M, this is R2. So 0 XOR with 0, 0. Again, these 3 XOR. So whatever may be the operation, all zeros means all zeros here. Next, when the input is 1, that is the next bit. So next shift operation will perform. So for the next shift operation, these contents of the flip-flops should be considered as the previous values for this operation. So that's why write all these 3 once again here. Now this will be the previous values for the current shift operation. So when you perform shift operation and find the contents again by using the same formulas, so that R0 dash is equal to M XOR with R2. M XOR with R2. So 1 XOR with 0, that is 1. You know that. Next, R1 dash is equal to M XOR with R2 XOR with R0. So M XOR with R2 XOR with R0. So 1 0 0. So XOR operation is 1 because for odd number of ones output will be 0 1 and even number of ones output will be 0 for XOR operation. So based on that you can identify the outputs. Next, R2 dash is nothing but equal to R1. R2 dash is equal to R1. What is R1 here? 0. So same will be repeated. Next, the third message bit input is 0, 0. So for this shift operation, these contents will be considered as the previous values. So repeat this once again here, and based on these 4 values, find the next values. So R0 dash is equal to once again M XOR with R2, that is 0, and R1 dash is equal to M XOR with R2 XOR with R1 R0. So these 3 values XOR is equal to 1. Next, R2 dash is equal to R1. What is R1 here? 1. So 1 will be there. Again, the last input bit is 1. So this will be considered as the previous values here, 0, 1, 1. So that the final contents of the flip-flop are R0 dash is equal to M XOR with R2. So 1 XOR with 1, that is 0. Next, these 3, again 0. And R2 dash is equal to R1. So that is 1. So finally, observe that 0, 0, 1 are the contents of these 3 flip-flops after all the shift operations coming from the message bits. So then the output will be taken from this last stage, so that the last flip-flop content will come first, and then R1 content will come first, second, and then R0 content will come after that. So that's why we need to write these bits in a reverse way. So let us consider this is LSB and MSB, so that first message bits will come as it is in the form of code word, that is 0101 will come directly. After that, these flip-flop contents will come in a reverse way, that is first write 100. So 100. So 4 plus 3, that is 7-bit code, or a 7-bit code. This is what the complete operation of cyclic encoder, and as well as calculation of the parity bits from this encoder, and final writing the encoder output as a code. Okay, so this is the way to find the code word for a particular given message by using this encoder diagram. Okay, so you should be able to perform this kind of operation whenever the input changes. So bits will be changes, so the operation will changes. And similarly, you should be able to draw these encoder diagrams for different generator polynomial equations. Okay, by using the same procedure, right? For example, if you want to draw the encoder diagram for this particular generator sequence, so what are the steps we already follow? The first step is identifying the number of flip-flops that must be there in the encoder diagram. The number of flip-flops will be identified from the last highest component. So here it is 4. So there will be 4 flip-flops. So first draw the 4 flip-flops as a boxes like this. So 1, 2, 3, 4. So 4 flip-flops will be there. Okay. And what is the second step? So in that, just represent with notations like R0, R1, R2, or whatever maybe the notation you want, you can write. So 4 flip-flops are there. Second step is identifying the coefficients of the generator polynomial equation. So how to identify that? We know that first term and last term don't have coefficients. In between only there will be coefficients. That is, if x term is there, so there is one coefficient, that is G1 is equal to 1. If x square term is there, so G2 is equal to 1. But here there is no x square term. There is no x square term, so G2 is equal to 0. Next, G3. If x cube term is there, there will be G3. So x cube term is there. Okay. So G3 is equal to 1. There are no G4 because the last component doesn't have coefficient. So only 3 coefficients are identified. So based on the coefficients, we should draw the feedback connections. But before that, the second step is connect the last flip-flop and make an XOR operation with the message bits. Okay, the last flip-flop output must be make an XOR operation with the message bits, and you should connect that output to the first flip-flop. That is the second step. And third step will be connecting this feedback path based on these coefficients. If there is a coefficient, there is a first coefficient. So since first coefficient is identified as C1 is equal to 1, so if there is a coefficient, so there will be a connection to this from the feedback path. So connect this feedback path, make an XOR operation with the first flip-flop output, and then connect to the next flip-flop. Next, since G2 is 0, so there should be no connection. It is open circuited. So no connection, no XOR operation. So it is directly connected to R2. Next, G3 is equal to 1. So there is a coefficient here. G3 is equal to 1. So if there is a coefficient, you should connect the feedback path and make an XOR operation with the flip-flop output and then connect to the next flip-flop. That's it. This is the simple implementation of a cyclic encoder diagram. So based on this particular encoder diagram, you can perform this kind of operations so that you should be able to, or you can easily find the encoder output by calculating the parity bits. Just write the message bits first as it is and then represent this parity bits in a reverse. That's it. That is the final calculation of code word from the cyclic encoder. So this is what the design and operation and finding the code word from the cyclic encoder. And the next thing is design of a syndrome calculator. Okay, this is going to be very simple. Design of syndrome calculator for cyclic codes for the purpose of decoding process. So now we enter into the decoding of cyclic codes. So in order to perform decoding operation, the first step is to calculate the syndrome vector. Okay, to calculate the syndrome vector. Based on the syndrome vector only, it is possible to decode finally. So let us define what is syndrome. So syndrome value contains some vector. It is nothing but a vector having some bits like this. So like this, it is having some bit sequence. So based on that vector, we will be able to decode the cyclic codes. So let us see how it is possible. And before that, you should be able to design the syndrome calculator circuit similar to the encoder circuit here. Okay, similar to the encoder circuit here. So it is very easy to design the syndrome calculator because if you observe, this is the encoder diagram, then the syndrome diagram will be just as like the same diagram. So this diagram is exactly same, but only the difference is instead of having an XOR operation at the last flip-flop output, there will be an XOR operation at the first flip-flop input. So just replace this XOR operation at the starting point. So then this diagram will become the syndrome calculator diagram. So no need of further understanding, no need to involve deeply. Just replace this XOR operation from that last flip-flop output to first flip-flop input. That's it. Okay. So now you can clearly observe what is the syndrome calculator diagram. So there is no XOR operation at the last flip-flop output. So again, assume this will be some flip-flops, but representation may be with some other variable like S0, S1, S2, and so on. Again, the feedback connections are already same. So instead of using XOR operation at the last stage, there will be XOR operation at the first stage. But the XOR operation with what? In the encoder, the XOR operation with message bits. But in the syndrome calculator for the decoding purpose, it should make an XOR operation with the received code vector. So whatever the code vector or a code what you are receiving at the receiver side, okay, here the decoding means we identified that after this encoder, this is the code word what we generated. This is what the encoder output. Okay, so this output is going to be transmitted, and in the receiver section, the same thing we must receive, right? But due to the noise or errors in the channel, this is received as a error. That means some of the bits may be erroneous. That means instead of 0, it may be received as 1, but instead of 1, it may be received as 0. That means that received code vector may contain errors. So we need to identify the errors, we need to detect that errors, and we need to correct that errors finally. So for the purpose of that, we should use this syndrome diagram to calculate the syndrome. Based on the syndrome vector only, we can able to it is possible to find the errors. Okay, here in the encoder diagram, we calculated that number of parity bits from the contents of these flip-flops. So here also the contents of these flip-flops are nothing but the syndrome vector. corresponding bits is equal to syndrome vector. That's it. Okay. So here XOR operation is shifted to input side and make an XOR operation of received vector and the feedback path and then follow the same diagram. Okay. So here also you can follow the same procedure. The first step is identify the number of flip-flops required based on the number of parity bits. So draw the blocks based on the number of flip-flops, and then here instead of connecting this first XOR at the last stage, connect the XOR at the first stage. Connect the XOR at the first stage and then make a feedback path to the last output, and then connect the feedback connections. Okay, depending on the number of portions involved. So here I am using the same generator polynomial equation, and for the same input we'll find the, we have already find the encoder output. So here this will be the syndrome calculator. So if you can clearly observe, again there will be 3 flip-flops because there will be 3 parity bits. So from the 3 parity bits we identified that 3 flip-flops are there. So connect, second step is connect this XOR operation with the received code vector, that is Y. Here what is Y? We already encoded the output from the cyclic encoder and that is transmitted in the channel. In the channel there will be some errors. So that 7-bit data may be received as errors. It may contain errors or may not contain errors. We need to identify whether it is having error or not. So that received code vector at the receiver side is considered as Y. So that Y make an XOR operation with this feedback path. So this feedback input must be connected to the last flip-flop output. So this output must come to here and make an XOR operation. This first flip-flop, and this output must be connected to the feedback path. If there is a coefficient, connect this. If there is no coefficient, disconnect this. Since it is the same diagram with same equation, so this is the same shift register diagram. Again, there will be a same operation, but here instead of using this message bits, we should use received bits. So this 7-bit received bits, one after the other, should make an XOR operation. Again, S0, S1, S2 are the register content before shift operation, and S0 dash, S1 dash, S2 dash are nothing but shift register contents after shift operation. Again, from the previous explanation or previous operation of encoder, here also perform the same operation. So first identify what are the values of S0, S1 dash, S0 dash, S2 dash. So what is S0 dash? How to find the content of S0? It comes from this particular input. So how input is calculated? It's nothing but XOR operation of this and this one. So that means XOR operation of Y and XOR operation of S2. Okay. So Y XOR with X2. Next, S1 dash. What is the content of S1 after shift operation? That is comes from this input. So this is nothing but XOR operation of S0 and S2. So S0 XOR with S. This is S2. Okay, I'll have to remember this is S2, right? Because S0 content, S1 content will come from S0 and then S2 feedback path, right? So that S1 dash is equal to S0 XOR with S2. Next, and then S2 dash. What is S2 dash? S1 is directly connected to S2, so that S2 dash is equal to S1. So again by using the same formulas, apply here. Assume the flip-flop contents before shift operation are all are zeros, and for every received bit there will be a one shift operation. So this shift operation, after the shift operation, the shift register contents are flip-flop contents are calculated by using the formulas. Okay. So apply these formulas. So S0 dash is equal to Y XOR with S2. So here it is Y XOR with S2. That is 1 XOR with 0. That is 1, and so on. We'll calculate for every next shift operation. Consider these values are the previous values. So repeat here 1 0 0, and based on these 4 values, perform the shift operation. Substitute in the formulas and find the contents of S0, S1, S2. After every shift operation based on these inputs, after completing the last input from the received bit, so that the final contents of the flip-flops are nothing but syndrome values. So that is 101. If you write in reverse way also, it is 101. So this is what the syndrome vector, which is identified as 101. So anyway, we have identified the syndrome vector from the syndrome calculator diagram or syndrome calculator shift register diagram. So then what next? Okay, but here the problem is detect and correct errors in the received code word using syndrome calculator and then decode the data. Okay, so we need to detect, we need to identify the errors and we need to correct the errors by using this diagram, and we need to decode the data also. So for that purpose, the first step is, after designing the syndrome calculator, by using this operation, you should perform and calculate the syndrome vector. So first step is calculation of syndrome vector. So based on the syndrome vector, how to detect and correct errors. Okay, this is the procedure. That is what the decoding procedure for error detection and correction. So from the received code vector, the first step is calculate the syndrome vector from the syndrome calculator diagram. So if the syndrome vector is identified as 101, whatever be the value, so that must be compared in the lookup table. So this lookup table is a database for a cyclic codes. In that database, there will be some different error patterns. So if you observe that, the error pattern will be same as that of 7-bit sequence. If it is a 7,4 cyclic code, for that 7,4 cyclic code, output will be 7 bits. So again, error pattern also containing 7 bits. All are zeros except there will be one at a corresponding error position. So that means this error pattern represents that whenever there is a 1, so that position indicates there is an error. For example, this is the 4th bit position. If the syndrome vector is 110, after we calculated from this operation, if the syndrome vector is found to be 110, then it is clear that we can clearly conclude that there will be an error in the 4th bit position, because we compared in the lookup table and identify that error pattern will be like this. So 1 will be obtained at the 4th bit position. So this error pattern indicates that there will be an error in the 4th bit position. Or else if you observe the syndrome vector as 0, 1, 1, so it indicates that the error will be in the 2nd bit position. Or else if the syndrome vector is 1, 1, 1, so there is an error in the 2nd bit position. Similarly, if the syndrome vector is already calculated as 101, so it indicates that there will be an error in the 1st bit position. So now we can verify. Now we can verify whether there is an error in the 1st bit or not. Okay. So we identified that there is an error in the 1st bit. That means instead of 0, we are receiving this as 1. Okay. So let us verify with what is the code word we already transmitted. What is the code word we already transmitted? That is 0101 But what it is coming? Instead of 0101, it is 1101 and 10. So that means instead of 0, it is receiving it as 1. So without having this knowledge, we identified that there is an error in the 1st bit position by comparing the lookup table, right? So that is the identification of error. It is identified that this is the 1st bit error. So corresponding error pattern is 1 and remaining all are zeros. So make an XOR operation of this received code vector and this error pattern, so that the error will be automatically corrected. Because when one XOR operated with this 1st bit, that is 1, automatically one XOR with 1 will be 0. Remaining will be as it is. So this is what the corrected data. And then if you finally want to identify the decoded message bits, so just remove these parity bits so that the remaining 4 bits will be message bits. So that is what the original message bits that is decoded by using this syndrome decoding process and from the syndrome calculator. Okay. So that is the explanation and the analysis of encoder for cyclic codes, design of encoder for cyclic codes, and design of syndrome calculator and decoding process related to cyclic codes. I hope you understand all the concepts. So thank you very much.